Hello there, and welcome to Sleepy Answers. Tonight, we're embarking on a quiet journey into one of the most profound mysteries humanity has ever contemplated. We're going to drift back through time, through millions of years, to answer a question that seems simple, but opens into endless wonder. Who was the first human? Before we begin this gentle exploration through deep time, I want to invite you to like this video and subscribe to the channel if you enjoy these peaceful journeys through science and discovery. Your support helps more curious minds find their way here, one sleepy soul at a time. But for now, all you need to do is settle in. Let your body relax. Allow your mind to wander backward through time, and let's begin this extraordinary story together. The question of who was first seems straightforward enough. We want a name, a face, a moment when the first true human drew breath and looked out at the world with newly human eyes. We want to point to a specific individual and say, "There, that was the beginning of us." But, as we'll discover tonight, the answer isn't that simple. It never is when we peer into the deep past. The story of our origins unfolds not as a single moment, but as a long, winding river of change, flowing across millions of years, branching and merging, full of cousins and ancestors, dead ends and new beginnings. When we ask who the first human was, we're really asking several questions at once. Are we asking about the first member of our species, Homo Sapiens? Or are we asking about the first member of our genus, Homo, which includes many species that walked the earth before us? Or perhaps we're asking about something even broader. When did our ancestors first become recognizably human-like, walking upright, using tools, building communities, thinking thoughts that would one day lead to art and language, and the very question we're asking now? The truth is that there was no first human in the way we might imagine. There was no sudden transformation, no magical moment when an ape gave birth to something entirely new. Instead, our lineage emerged through an incredibly slow process of change, so gradual that if you could line up every generation from our distant ancestors to the present, you couldn't point to the place where one species ended and another began. Each child was almost exactly like its parents, but over thousands and millions of generations, those tiny changes accumulated into something remarkable. Us. Tonight, we'll meet the ancestors and relatives who populate our family tree. We'll walk alongside Lucy, who lived over 3 million years ago, and taught us that our ancestors walked upright long before they developed large brains. We'll encounter Homo erectus, the great traveler who first left Africa and learned to control fire. We'll meet the Neanderthals, our closest cousins, whose DNA still flows in the veins of most people alive today. And we'll trace the emergence of our own species, Homo sapiens, from the African continent roughly 300,000 years ago. This journey will take us through a landscape populated not by a single line of ancestors marching steadily toward modernity, but by a rich forest of different human species, many branches of the human family, some of which thrived for hundreds of thousands of years before fading away. Our story is not one of inevitable progress, but of adaptation, survival, luck, and the countless small moments that accumulated over eons led to the emergence of the only human species still walking the earth today. As you listen, Imagine yourself standing at the edge of this vast expanse of time. Behind you stretches the entire history of our species, a mere eye blink in geological terms. Before you lies the immense corridor of deep time, reaching back through ice ages and warm periods, through dramatic climate shifts and changing landscapes, all the way to the distant moment when our ancestors first began the journey that would eventually lead to us. Let yourself drift into that landscape. Let the millions of years wash over you like waves, each one carrying stories of beings who lived and died, loved and feared, struggled and succeeded in a world almost unimaginably different from our own. The deep past, before the first humans. To understand where humans came from, we need to go back further than you might expect. We need to return to a time when our ancestors weren't human at all, when they were still part of the great ape family, moving through the forests of Africa on 4 limbs, their futures unwritten, their potential still hidden in their genes. The story begins somewhere between 6 and 7 million years ago. This is when our lineage split from the lineage that would lead to chimpanzees and bonobos, our closest living relatives. This split wasn't dramatic. It wasn't a single event, but a process that unfolded over time as populations became separated, perhaps by geographical barriers like rivers or mountains, perhaps by subtle shifts in climate that changed the distribution of forests and open lands. Slowly, imperceptibly at first, these separated populations began to change in different ways, accumulating different mutations, adapting to slightly different environments, until they could no longer interbreed, until they were no longer the same species. Finding fossils from this crucial period is extraordinarily difficult. Fossils require very specific conditions to form. Most creatures that die are consumed by scavengers, scattered by wind and water, broken down by bacteria and time. Only rarely does a body come to rest in conditions that allow it to be preserved. And even then, it must survive millions of years of geological processes, only to be discovered by someone who recognizes what they've found. It's a miracle that we have any fossils at all from this period, and the ones we do have are often fragmentary, tantalizing glimpses rather than complete pictures. One of the oldest possible members of our lineage is Sahelanthropus tecadensis, known from a skull discovered in Chad and dated to between 6 and 7 million years ago. The skull is remarkable, combining features that look ape-like with others that seem more human-like. Its canine teeth are relatively small, unlike the large stabbing canines of modern apes. The position of the foramen magnum, the hole where the spine connects to the skull, suggests that this creature might have walked upright, at least sometimes. But we don't have any limb bones, so we can't be certain. Was Sahelanthropus one of our ancestors, or was it on a side branch that led nowhere? The debate continues, and without more fossils, we may never know for sure. Then there's Ororin tuganensis, the so-called Millennium Man, found in Kenya and dated to about 6 million years ago. This species is known from fragmentary remains, including a thigh bone that seems to show adaptations for upright walking. The shape of the bone, its thickness, and the angle at which it would have met the hip all suggest that Orrin spent at least some time walking on two legs. Again, though, the evidence is incomplete, and scientists disagree about whether Orrin was truly on the line leading to humans or represents another experiment in upright walking that ultimately didn't lead to us. Ardipithecus ramidus, known from fossils in Ethiopia dated to about 4.5 million years ago, gives us a more complete picture, though still a puzzling one. The most famous Ardipithecus fossil, nicknamed Ardi, preserves much of a skeleton, allowing scientists to reconstruct how this creature might have moved. Ardi had a strange mix of features. She could walk upright, but not in the same efficient way that later hominins would. Her feet retained a grasping big toe, useful for climbing trees but not ideal for walking long distances on the ground. Her arms were long, suggesting she spent considerable time in the trees. Her canine teeth were reduced compared to apes, hinting at changes in social behavior and diet. Ardipithecus challenges many of our assumptions about human evolution. For years, scientists thought our ancestors evolved in an environment of expanding grasslands, that the need to walk upright emerged as forests gave way to savannas. But Ardipithecus lived in a wooded environment, suggesting that upright walking might have evolved for reasons other than adapting to open country. Perhaps it allowed for more efficient movement between widely spaced fruit trees. Perhaps it helped in wading through shallow water. Perhaps it freed the hands for carrying food or offspring. The truth is, we don't know for certain, and that uncertainty reminds us how much remains mysterious about our origins. These early creatures, whether they were our direct ancestors or not, set the stage for what came next. They demonstrate that the transition from ape to human was not a single leap, but a gradual process involving many different lineages, many experiments in upright walking and new ways of living. Some of these lineages led nowhere, ending in extinction after thousands or millions of years. Others contributed to the river of evolution that would eventually flow toward us. The landscape of Africa during this period was in constant flux. The climate oscillated between wetter and drier periods. Forests expanded and contracted. Lake levels rose and fell. Mountain ranges continued to rise, creating new rain shadows and dry zones. The East African Rift Valley, that great wound in the continent, was pulling apart, creating new habitats and isolating populations. In this dynamic environment, evolution proceeded not along a single smooth path, but in bursts and experiments, with different populations adapting to different conditions. Sometimes meeting and interbreeding, sometimes remaining isolated for hundreds of thousands of years. By 4 million years ago, creatures that we can more confidently call our ancestors were walking the African landscape. They were still not human in the way we would recognize, but they were becoming something new, something that had never existed before. They were becoming bipedal, fully committed to walking upright, and in that commitment lay the seeds of all that would follow. Because once you're walking on 2 legs, your hands are free for other tasks. You can carry things. You can manipulate objects with precision. You can make tools. And with tools comes the need for a more complex brain to use them effectively. and with a more complex brain comes the possibility of language, culture, art, and all the things that make us human. The Australopithecines, our upright ancestors. Around 4 million years ago, a group of creatures appeared in Africa that paleontologists call the Australopithecines, the southern apes, named after the first specimens discovered in South Africa in the 1920s. These weren't apes, and they weren't quite human, but they represent a crucial stage in our evolution. The stage where upright walking became the dominant mode of movement, where our ancestors committed fully to life on 2 legs. The earliest of these Australopithecines that we're relatively certain about is Australopithecus anamensis, which lived between about 4.3 and 3.8 million years ago in East Africa, particularly in what is now Kenya and Ethiopia. Known from fragmentary remains including jaws, teeth, and some limb bones, Australopithecus anamensis shows clear adaptations for upright walking while retaining some primitive features. The arm bones suggest these creatures were still capable climbers, but the leg bones tell a different story. They're built for bipedalism, with features that indicate these creatures could walk upright efficiently for considerable distances. A nearly complete skull of Australopithecus anamensis discovered in recent years has given scientists their first look at the face of this ancient ancestor. It's a face that combines bear-like and human-like features in ways that help us understand the transition between these 2 states. The skull is smaller than a modern human's, reflecting a brain about the size of a chimpanzee's. The face projects forward, with a relatively flat nose and prominent jaw. Yet, the position of features related to upright walking are distinctly human-like. But if we're talking about Australopithecines, we must talk about the most famous one of all, the individual who has probably done more to capture public imagination about human evolution than any other fossil. Lucy. Lucy was discovered on November 24, 1974, in the Afar region of Ethiopia by paleontologist Donald Johansen and his team. Johansen was out surveying with graduate student Tom Gray when he spotted a piece of an arm bone lying on the surface. Looking around, he saw more bones, fragments glinting in the afternoon sun, scattered across the slope. What they had found was extraordinary, about 40% of a single individual skeleton, an unprecedented level of completeness for a fossil of this age. That night, back at camp, the team celebrated their discovery. Someone played a cassette tape, and the Beatles' song "Lucy in the Sky with Diamonds" echoed across the Ethiopian landscape. At some point during the celebration, someone suggested they name the fossil Lucy, and the name stuck. Though she's also known by her Ethiopian name, Dinknesh, meaning "you are marvelous," to the world she became Lucy. And Lucy she has remained for 50 years. Lucy's formal designation is AL-288-R1, indicating she was the first significant find from Afar locality 288. She lived about 3.2 million years ago, and her skeleton has taught us more about human evolution than perhaps any other single fossil. She stood about 3 feet 7 inches tall when alive and weighed perhaps 64 pounds, roughly the size of a small adult chimpanzee. But unlike a chimpanzee, Lucy walked upright. The evidence for this is written in her bones. Her pelvis is shorter and broader than an ape's, providing better support for upright posture and creating a more efficient platform for the muscles that stabilize the body during walking. Her femur, the thigh bone, is angled inward so that her knees would have been closer together under her body, exactly as in modern humans, allowing for a more efficient walking gait. Her foot, while not complete in the fossil, shows evidence that her big toe was aligned with her other toes rather than being opposable, like an ape's grasping foot. She was built for walking. Yet Lucy retained many primitive features that remind us she was not human. Her arms were long relative to her legs, suggesting she might have spent time in trees, though scientists debate how much. Her hands had curved fingers that would have been useful for grasping branches. Her rib cage was cone-shaped like an ape's rather than barrel-shaped like a human's, suggesting her internal organs were arranged differently. And her skull, small and primitive, housed a brain only slightly larger than a chimpanzee's, about 400 cubic centimeters compared to the 300 to 1,500 cubic centimeters of a modern human brain. Lucy's species, Australopithecus afarensis, was first formally described in 1978, 4 years after her discovery. The name combines Australopithecus, meaning southern ape, with afarensis, referring to the Afar region where she was found. By this time, Johansen and his colleagues had discovered many more fossils of this species, including a remarkable site called AL333, nicknamed the First Family, where the remains of at least 13 individuals were found together, possibly the victims of a single catastrophe like a flash flood. With hundreds of specimens now known, Australopithecus afarensis is one of the best represented species of early human ancestor in the fossil record. These fossils reveal a species that existed for nearly 1 million years, from about 3.85 to 2.95 million years ago. An impressive run that's more than 4 times as long as our own species has been around. During that immense span of time, Australopithecus afarensis witnessed dramatic environmental changes as Africa's climate fluctuated between wetter and drier periods. Yet the species persisted, adapting to changing conditions. One of the most extraordinary discoveries associated with Australopithecus afarensis isn't even a fossil. It's footprints. At a site called Laetoli in Tanzania, about 1,000 miles from where Lucy was found, paleontologist Mary Leakey and her team discovered something remarkable in 1976. A trail of fossilized footprints preserved in volcanic ash, dated to 3.6 million years ago. The footprints were made by hominins, walking through a layer of ash that had settled on the ground after a volcanic eruption. Soon after they walked through, rain fell, turning the ash to something like cement, and their footprints were preserved. The Laetoli footprints are hauntingly human. They show a foot with a non-opposable big toe aligned with the other toes, a rounded heel, and a longitudinal arch, all features of feet designed for upright walking. The stride and gait pattern revealed by the footprints are remarkably similar to those of modern humans. 2 individuals, one larger and one smaller, walked together, their footprints sometimes overlapping. Some researchers have even suggested that a third, smaller individual walked in the footprints of the larger one, perhaps a child stepping in a parent's tracks. Though we can't be certain the Laetoli prints were made by Australopithecus afarensis specifically, fossils of that species have been found in the region from around the same time, making them the most likely candidates. These footprints give us something that fossils alone cannot: a glimpse of behavior, of movement, of life as it was lived. They remind us that these weren't just bones, scattered across the landscape millions of years later. They were living, breathing creatures who walked across a volcanic plain on a day when rain was coming, who moved with purpose, who may have walked together as a family or group. The footprints speak to us across the immense gulf of time, connecting us to individuals whose names we'll never know but whose journey led eventually to us. Lucy's species was not alone on the landscape. Recent discoveries have revealed that the 3-million-year mark was a time of remarkable diversity among early hominins. In 2012, paleontologist Johannes Haile Selassie and his colleagues announced the discovery of a foot from a hominin dated to 3.4 million years ago, contemporaneous with Lucy's species. But this foot was fundamentally different. Its big toe was divergent, able to grasp like an ape's foot, suited for climbing rather than efficient walking. Without associated skull or dental remains, the researchers couldn't confidently assign this foot to a species, but it proved beyond doubt that Lucy's kind shared the landscape with at least one other very different hominin. Then, in 2015, Haile Selassie's team announced another discovery: fossilized jaws and teeth from a species they named Australopithecus diarrhea, meaning close relative in the Afar language. These fossils, dated between 3.5 and 3.3 million years ago, came from the same region where Australopithecus afarensis fossils had been found. The teeth and jaw structure are different enough to clearly represent a distinct species, proving that at least two species of Australopithecines coexisted in the same area during Lucy's time. This growing picture of diversity has transformed our understanding of human evolution. For years after Lucy's discovery, many scientists thought of Australopithecus afarensis as a sort of central trunk in the human family tree, the last common ancestor from which later hominins, including our genus Homo, descended. But the reality appears to have been far more complex, with multiple species existing simultaneously, experimenting with different ways of being a bipedal ape, different diets, different behaviors, different survival strategies. Lucy's species was successful, lasting for nearly 1 million years, but it was part of a diverse community of hominins, not a lonely march toward modernity. Recent research has also complicated our understanding of how Lucy and her kind lived. For decades, scientists assumed that because these creatures were bipedal, they had abandoned the trees entirely in favor of life on the ground. But detailed analysis of Lucy's skeleton and others from her species suggests a more nuanced picture. While they were certainly capable of walking long distances on the ground, the proportions of their limbs, the curvature of their fingers, and the structure of their shoulders all suggest they retained the ability to climb trees efficiently. Perhaps they slept in trees for safety from predators. Perhaps they foraged for fruits in the canopy. Perhaps young individuals spent more time in trees than adults. The picture is of creatures in transition, committed to bipedalism but not yet fully terrestrial in the way that later humans would be. Understanding how Lucy died adds another poignant dimension to her story. In 2016, researchers published an analysis of CT scans of Lucy's bones, revealing fractures in her arms, legs, and shoulder consistent with injuries sustained in a fall from a significant height. The pattern of breaks suggested she had reached out her arms to break her fall, causing the kind of fractures seen in humans who fall from trees or buildings. The researchers proposed that Lucy fell from a tree, perhaps while sleeping or foraging, and that the impact killed her or left her badly injured enough to die soon after. It's impossible to know for certain, and other scientists have proposed alternative explanations for the fractures. But the possibility that Lucy's life ended with a fall adds a strange intimacy to our connection with this ancient ancestor. She might have died in a moment of fear and pain, reaching out to break her fall, just as any of us might do. The Australopithecines, with Lucy as their most famous representative, teach us something fundamental about human evolution. We didn't start with big brains. Intelligence didn't lead the way. Instead, our ancestors first committed to walking upright, and only later, much later, did brain size begin to increase dramatically. This sequence has important implications. Walking upright freed the hands, and free hands could carry things, could manipulate objects with precision, could eventually create and use tools. The selective pressures that favored increasingly dexterous hands and the complex brain circuitry needed to control them came after bipedalism was already established. We walked first and thought later. The dawn of Homo, when we became human. The boundary between the Australopithecines and our own genus, Homo, is frustratingly blurry. There's no clear dividing line, no moment when one species gave birth to something obviously different. Instead, fossils from around 2.5 to 3 million years ago show a confusing mix of features, some still Australopith-like, others beginning to show characteristics we associate with the genus Homo. It's during this period, in this transitional fog, that our own genus emerged. The earliest fossil that has been assigned to the genus Homo is a partial jawbone from Ethiopia dated to about 2.8 million years ago. This fossil, designated LD 350-1, was announced in 2015 and immediately sparked debate. Is it really Homo, or is it a late Australopithecine with some Homo-like features? The fossil is fragmentary, making definitive assignment difficult, but its discovery pushed the origin of our genus back in time and showed that the transition was happening in East Africa at a time of significant environmental change. Around 2.6 million years ago, something new appears in the archaeological record. Stone tools. These aren't natural rocks, but stones that have been deliberately struck to create sharp edges. Tools that could be used to butcher animals, process plant materials, or accomplish other tasks that required a cutting edge. The oldest confirmed stone tools come from a site called Gona in Ethiopia and are simple but unmistakably intentional. Slightly younger tools from another Ethiopian site called Lomekwi push the origin of tool use even further back to 3.3 million years ago, though these older tools may have been made by Australopithecines rather than by members of genus Homo. The appearance of stone tools marks a profound shift in how our ancestors interacted with their environment. A sharp stone tool extends the capabilities of the hand, allowing our ancestors to access foods that would otherwise be difficult to process. With tools, they could butcher large animal carcasses, cutting through tough hide to access nutritious meat and marrow. They could process fibrous plants, dig for roots and tubers, scrape, and prepare hides. Tools opened up new dietary options, and diet affects everything from brain development to social organization. Two species of early Homo that appear around 2 million years ago are Homo habilis and Homo rudolfensis. Both are known from fragmentary fossils found in East Africa, and both show characteristics that distinguish them from the Australopithecines, while still retaining many primitive features. Homo habilis, whose name means handy man, was originally associated with the stone tools found in the same deposits, though we now know that tool use may have predated this species. Homo habilis had a brain slightly larger than the Australopithecines, about 600 to 700 cubic centimeters, still much smaller than modern humans, but a step in the direction of increased brain size. The face was less projecting than in Australopithecines, and the teeth were somewhat smaller, suggesting dietary changes. The arms were still relatively long, and the exact pattern of locomotion remains debated, but Homo habilis seems to have been fully bipedal while perhaps retaining some climbing ability. Homo rudolfensis is known from even more fragmentary remains, primarily skulls and facial bones found near Lake Rudolph in Kenya, now called Lake Turkana. This species had a larger brain than Homo habilis, perhaps 700 to 800 cubic centimeters, and a flatter face. Some scientists question whether Homo rudolfensis is really a separate species or simply a large variant of Homo habilis, and the debate continues. What's clear is that around 2 million years ago, there were hominins in East Africa with brains noticeably larger than their Australopithecine predecessors, with different facial proportions, and associated with stone tool technology. But why did brain size start to increase at this particular moment in our evolutionary history? The answer likely involves a complex interaction of factors. Climate change was making Africa's environment more variable and unpredictable. The ability to adapt to changing conditions, to solve novel problems, to remember where food sources were located in a shifting landscape. These cognitive abilities would have been increasingly valuable. Access to more nutritious foods, including meat obtained through hunting or scavenging, and processed with stone tools, would have provided the energy needed to support larger, more metabolically expensive brains. Social complexity may have been increasing, creating selective pressures for better communication, cooperation, and the ability to navigate complex social relationships. Larger brains, in turn, would have created new challenges. A bigger brain requires more energy, meaning mothers needed better nutrition to support pregnancy and nursing. The birth process becomes more difficult with larger infant heads, creating selective pressure for physiological adaptations like birth at an earlier stage of development when the infant's brain is still relatively small. This means human infants are more helpless at birth than those of most other primates, requiring extended parental care, which in turn creates pressures for stable pair bonds and cooperative child-rearing. Larger brains also take longer to grow and develop, extending childhood and creating opportunities for learning, but also requiring resources be devoted to children for many years. The evolution of larger brains wasn't just a simple increase in size, but a transformation that rippled through every aspect of our ancestors' biology and behavior. One more thing about these early members of genus Homo deserves mention. They were still relatively small. Homo habilis and Homo rudolfensis weren't much larger than Lucy, perhaps 4 to 5 feet tall and weighing 80 to 100 pounds. They still had relatively long arms and features suggesting they were comfortable in trees. They weren't yet the tall, long-legged, fully terrestrial creatures that later humans would become. That transformation would come with the next major species in our lineage, one of the most successful and long-lived human species ever to walk the earth. Homo erectus, the great traveler. If you were to travel back in time 2 million years and encounter Homo erectus, you would recognize them as human in a way that you might not recognize the Australopithecines, or even the earlier members of genus Homo. Homo erectus stood tall, perhaps 5 to 6 feet in height, with body proportions that look fundamentally modern. Their arms were shorter relative to their legs. Their torso was narrow and barrel-shaped, and their long legs were built for covering distance efficiently. If you saw one walking in the distance, dressed in modern clothes, you might not immediately realize they were a different species. But come closer, and the differences would become apparent. The skull of Homo erectus is distinctive, with a low, flat forehead, thick brow ridges protruding above the eyes, and a projecting face. The skull is long and low, rather than high and rounded like ours. The brain, while larger than earlier hominins at about 900 to 1,100 cubic centimeters, is still significantly smaller than the modern human average. The jaw is large and robust, with bigger teeth than modern humans, though smaller than earlier hominins. Looking into their eyes, you might see intelligence and awareness, but you would also see something different, something not quite human in the way we understand it. Homo erectus first appears in the fossil record about 1.9 million years ago in East Africa. The species persisted for an astonishing length of time, with the most recent confirmed fossils dated to just over 100,000 years ago, meaning Homo erectus existed for nearly 2 million years. To put that in perspective, our own species has been around for perhaps 300,000 years. Homo erectus was successful in ways that we're only beginning to understand, adapting to diverse environments, surviving through numerous climate shifts, and eventually spreading far beyond Africa. One of the most remarkable things about Homo erectus is that they were the first hominins to leave Africa. Around 1.8 million years ago, Homo erectus populations began moving into Asia and eventually Europe. We find their fossils in Georgia, in China, on the Indonesian island of Java, across a vast geographical range. How and why they dispersed so widely remains a subject of research and debate, but the expansion represents a fundamental shift in the human story. Our ancestors were no longer confined to a single continent. They were becoming global. The famous Peking man fossils from China and Java man fossils from Indonesia are both Homo erectus. When these fossils were first discovered in the early 20th century, they were given different species names because scientists didn't realize they represented the same widespread species. It took decades of research and the discovery of many more fossils to understand that Homo erectus was not a local phenomenon, but a successful species that adapted to diverse environments across much of the Old World. What enabled Homo erectus to spread so successfully? Part of the answer surely lies in their body plan, which was built for efficient long-distance walking and running. With their long legs and narrow hips, they could cover ground effectively, allowing them to range over large territories in search of food and respond to environmental changes by moving to more favorable areas. But there's more to the story than just mobility. Homo erectus was the first hominin species for which we have strong evidence of controlled use of fire. The earliest definitive evidence of fire use comes from sites associated with Homo erectus in Africa and Asia, though the exact timing is debated, with claims ranging from 1.5 million years ago to more conservative estimates around 400,000 years ago. Controlled use of fire represents an enormous technological and cognitive leap. Fire provides warmth, allowing our ancestors to survive in colder climates. It provides protection from predators, as most animals fear fire. It provides light, extending the useful hours of the day into darkness. And, crucially, fire allows cooking. Cooking transforms food in ways that our ancestors couldn't have failed to notice. Cooked meat is easier to chew and digest, making more calories available from the same amount of food. Cooked plant materials are often safer, as cooking destroys many toxins and parasites. Some anthropologists have argued that cooking was essential to support the larger brains that characterize Homo erectus and later humans, as cooked food provides more readily available calories, reducing the gut size needed to process a food and freeing up energy for the metabolically expensive brain. The stone tools associated with Homo erectus also show significant advancement over earlier tools. Around 1.7 million years ago, a new tool technology appears in the archaeological record: the Acheulean hand axe. These are large, teardrop-shaped tools flaked on both sides to create a sharp edge all around. Making an Acheulean hand axe requires planning, skill, and the ability to hold a mental image of the desired end product while executing a complex series of strikes. The symmetry and refinement of these tools suggest a level of cognitive sophistication beyond what was required for the simpler Oldowan tools of earlier hominins. Remarkably, the Acheulean hand axe tradition persisted for over 1 million years, with relatively little change. You find these tools in Africa, Europe, and Western Asia, manufactured with remarkable consistency across vast distances and time spans. This suggests the existence of cultural transmission, with individuals learning to make these tools from others in their group and passing that knowledge to the next generation. It's possible that language, or at least some form of complex communication, was emerging during this period, though we have no way to know for certain. Homo erectus also shows evidence of caring for disabled or injured individuals. Several Homo erectus fossils show signs of severe injuries or disabilities that would have been debilitating. Yet the individuals survived for years after the injury, suggesting they were cared for by their group. One famous fossil from Dmanisi in Georgia shows an elderly individual who had lost all but one tooth, meaning they couldn't have chewed tough food effectively. Yet they lived for some time after losing their teeth, implying others in the group must have provided them with soft food or otherwise assisted them. Such evidence hints at the emergence of compassion, social bonds, and mutual support, behaviors that would become increasingly important in later human societies. Despite their long success, Homo erectus eventually disappeared. The latest confirmed fossils date to just over 100,000 years ago, by which time our own species, Homo sapiens, had already emerged and was beginning to spread. Why Homo erectus went extinct remains unclear. They may have been outcompeted by later human species with larger brains and more sophisticated technology. Climate change may have stressed their populations. They may have been absorbed through an interbreeding with other human species, their genes surviving even as their distinct identity disappeared. Or it may have been a combination of factors, different in different regions, a complicated end to a remarkable run. What's clear is that Homo erectus occupies a crucial position in human evolution. They were almost certainly our ancestors, or at least one of our ancestral species. Their body plan set the template for later humans. Their expansion out of Africa created the conditions for the emergence of other human species in different regions. Their technological innovations, from Acheulean hand axes to controlled fire, demonstrated cognitive abilities that would be built upon by their descendants. When we think about the deep history of our genus, Homo erectus stands as one of the central pillars, a species that thrived for nearly 2 million years and whose legacy flows through us. The middle chapter, Heidelbergensis and others. As we move forward in time from the era of Homo erectus, we enter what might be called the middle chapter of human evolution, a period from about 700,000 to 200,000 years ago, when several species of humans lived in different parts of the world, when brain size was increasing dramatically, and when the stage was being set for the emergence of both our species and our closest relatives. This period is marked by confusion and debate among paleontologists, because the fossils from this time often show intermediate characteristics, mixing features of Homo erectus with features that look more like modern humans or like Neanderthals. The question of how to classify these fossils, whether to lump them into a few species or split them into many, remains one of the most contentious issues in paleoanthropology. One species that many researchers recognize from this period is Homo heidelbergensis, named after a fossil jawbone found near Heidelberg, Germany in 1908. Homo heidelbergensis is thought by many paleontologists to be the last common ancestor of modern humans, Neanderthals, and possibly Denisovans. This species lived from perhaps 700,000 to 200,000 years ago, and had a brain size approaching that of modern humans, averaging around 1,200 cubic centimeters, larger than Homo erectus, but overlapping with the lower end of the modern human range. The skull of Homo heidelbergensis retains some primitive features, including prominent brow ridges and a receding forehead, but shows advancement toward more modern proportions. The face is less projecting than in Homo erectus, and the teeth are somewhat smaller. The body was robust and muscular, built for strength rather than endurance, running like earlier humans, suggesting adaptations to colder climates and perhaps different hunting strategies. Fossils assigned to Homo heidelbergensis or similar species have been found across Africa, Europe, and possibly Western Asia, suggesting this was a successful and widespread species. The famous Broken Hill skull from Zambia, sometimes called Homo rhodesiensis, but possibly just an African variant of Homo heidelbergensis, shows how these middle-period humans had spread across diverse environments. Similarly, fossils from Bodo in Ethiopia, dating to about 600,000 years ago, show features that link them to this broad group of archaic humans that were more advanced than Homo erectus, but not yet modern in the way that Homo sapiens would be. In Europe, fossils from the Cima de los Huesos, the pit of bones, in Spain's Atapuerca Mountains, have provided extraordinary insights into this period. This site, at the bottom of a cave shaft, contains the remains of at least 28 individuals who somehow ended up collected together, possibly deliberately placed there in what may represent some form of intentional burial or funerary practice, though this interpretation is debated. The fossils date to about 430,000 years ago, and remarkably, scientists have been able to extract ancient DNA from some of them, revealing that these individuals were early Neanderthals, ancestors of the classic Neanderthals that would later inhabit Europe and Western Asia. Another species from this period that deserves mention is Homo antecessor, known from fossils in Spain dated to about 800,000 years ago. These fossils show a mix of primitive and advanced features, and some researchers have proposed that Homo antecessor might represent a common ancestor of both Neanderthals and modern humans, predating the split between these lineages. However, the evidence is incomplete, and the evolutionary relationships remain uncertain. The picture that emerges from this middle period is one of considerable diversity. Different populations of humans existed in different regions, adapting to local conditions, evolving in partial isolation but probably maintaining some gene flow between populations. This wasn't a simple linear progression, but a complex network of related species and populations, sometimes separating, sometimes reconnecting, constantly changing in response to environmental pressures and random genetic drift. During this period, stone tool technology continued to advance. The Acheulean hand axe tradition that had dominated for over 1 million years began to be supplemented and eventually replaced by more sophisticated technologies. The Levallois technique, which appears around 300,000 years ago, involved careful preparation of a stone core to allow the removal of predetermined flake shapes, demonstrating planning and precision beyond what earlier technologies required. These prepared cores could produce multiple useful tools, making more efficient use of raw materials. There's also evidence of increasing behavioral complexity. Some sites show concentrations of animal bones, suggesting organized hunting of large game. There are hints of symbolic behavior, including the use of natural pigments like ochre, though the interpretation of such finds is often debated. The construction of shelters, the organization of living spaces, the long-distance transport of desirable stone materials for tool-making all point to increasingly complex cognition and social organization. Yet despite these advances, the humans of this middle period still weren't quite us. Their brains, while large, were shaped differently than ours, and presumably functioned somewhat differently. Their cultures, while more complex than those of earlier humans, lacked many of the features that would characterize later modern humans: elaborate art, musical instruments, sophisticated personal ornamentation, long-distance trade networks. They were sophisticated, successful, well adapted to their environments. But they weren't yet capable of the full range of symbolic and cultural behaviors that would characterize our species. This middle chapter set the stage for what came next. The populations living in Africa during this period would give rise to Homo sapiens. The populations in Europe would evolve into Neanderthals. Populations in Asia would follow their own evolutionary paths, including the mysterious Denisovans, known primarily from DNA rather than from abundant fossils. The human family tree was branching, with multiple species of humans existing simultaneously in different parts of the world, and setting up one of the most fascinating aspects of recent human evolution. When modern humans eventually left Africa, they would meet these other human species, and the encounters would leave lasting marks on our genomes. Our cousins, Neanderthals and Denisovans. By about 400,000 years ago, a distinct human species was emerging in Europe and Western Asia: the Neanderthals. Named after the Neander Valley in Germany, where the first recognized fossils were found in 1856, Neanderthals would become our most famous extinct relatives, the subject of endless fascination, speculation, and gradually increasing respect as we've learned more about their capabilities. Neanderthals were superbly adapted to the cold climates of Ice Age Europe. Their bodies were stocky and heavily muscled, with broad chests and short limbs, a body plan that conserves heat more effectively than the tall, linear build of many modern humans. They were incredibly strong, with robust bones that show prominent muscle attachment points, suggesting a life of intense physical activity. An average Neanderthal was probably significantly stronger than an average modern human, capable of feats of strength we would find remarkable. The Neanderthal skull is distinctive and instantly recognizable to anyone familiar with human fossils. The skull is long and low, with a characteristic bulge at the back called an occipital bun. The face is prominent, with a large nose that might have helped warm and humidify the cold air they breathed. Above the eyes are thick brow ridges, though less prominent than in Homo erectus. The forehead slopes backward rather than rising vertically as in modern humans. Yet despite these differences, the Neanderthal brain was actually slightly larger on average than the modern human brain, typically around 1/400 to 1/600 cubic centimeters, compared to our average of 1/300 to 1/500. For much of the 20th century, Neanderthals were portrayed as brutish, primitive, perhaps not fully human in behavior or cognition. This characterization was based partly on early misinterpretations of fossils, partly on cultural biases about what human ancestors should look like, and partly on incomplete evidence. As more fossils have been found and analyzed, as ancient DNA has revealed their genetic relationships to us, and as the archaeological record has been examined more carefully, the picture of Neanderthals has transformed dramatically. Neanderthals were sophisticated toolmakers, creating a stone tool technology called mosterian that involved careful preparation of stone cores and the production of a variety of specialized tools for different purposes. They hunted large game including mammoths, woolly rhinos, and giant deer, using wooden spears that required planning and cooperation to manufacture and deploy effectively. They controlled fire and built hearths, creating warm spaces in the cold caves and rock shelters they inhabited. They cared for their disabled and elderly, as evidenced by fossils showing individuals who survived severe injuries or reached old age despite being unable to fend for themselves. Most remarkably, Neanderthals engaged in symbolic behaviors that suggest a level of cognitive sophistication once thought unique to our species. They deliberately buried their dead, sometimes with grave goods, suggesting a concept of an afterlife or at least ritual practices surrounding death. They used pigments like ochre and manganese, possibly for body decoration or other symbolic purposes. They created objects with no obvious practical function, including a carved bone fragment with regularly spaced incisions that some researchers interpret as intentional marks, though others argue might be natural. Recent research has even provided evidence that Neanderthals created cave paintings in Spain, pushing back the date for symbolic art beyond the arrival of modern humans in Europe. Perhaps most intriguingly, there's evidence that Neanderthals may have had the capacity for speech. The hyoid bone, which supports the tongue and is important for speech, is preserved in some Neanderthal fossils and is virtually identical to ours. Analysis of the DNA related to brain development and language ability suggests Neanderthals shared many of the genetic foundations for language with modern humans. Whether they actually had spoken language comparable to ours remains debated, as language doesn't fossilize. But the anatomical and genetic evidence suggests it's quite possible. Despite their sophistication, Neanderthals disappeared. The last confirmed Neanderthal fossils date to about 40,000 years ago, with some disputed evidence pushing the date forward to perhaps 30,000 years ago in isolated populations. What happened to them remains one of the great mysteries of human evolution. Their disappearance coincides roughly with the arrival of modern humans in Europe, leading many to suspect that competition with Homo sapiens played a role. Perhaps modern humans had more efficient hunting strategies or better technology. Perhaps we were better at adapting to the rapidly changing climates of the period. Perhaps larger social networks among modern human groups provided advantages in resource acquisition or information sharing. Or perhaps the story is more subtle than simple replacement. We now know that Neanderthals and modern humans interbred. Most people of non-African ancestry carry about 1 to 4% Neanderthal DNA, inherited from interbreeding that occurred when modern humans first encountered Neanderthals in the Middle East and Europe, probably between 50,000 and 60,000 years ago. This means Neanderthals didn't entirely disappear. Their genes survive in us, contributing to traits ranging from immune function to skin and hair color to the shape of our noses. In a very real sense, Neanderthals are not extinct. They live on as a ghostly presence in our genomes. Even more mysterious are the Denisovans, a sister species to Neanderthals known primarily from DNA rather than from abundant fossils. The existence of Denisovans was discovered in one of the most remarkable scientific achievements of recent decades. The extraction and sequencing of ancient DNA from a tiny finger bone found in Denisova Cave in Siberia's Altai Mountains. When that DNA was sequenced, scientists realized they were looking at something unprecedented, a human species that was neither modern human nor Neanderthal, but something distinct, splitting from the Neanderthal line about 400,000 years ago. Subsequent DNA analysis of other fragmentary remains from Denisova Cave, including teeth and even tiny bone fragments identified through a new technique called collagen fingerprinting, confirmed the existence of this new human species. We still don't know what Denisovans looked like, as we have very few fossils. A partial skull from the Tibetan Plateau, identified through ancient protein analysis, and the fragmentary remains from Denisova Cave provide only limited anatomical information. But DNA tells us much about their distribution and interactions with other human species. Denisovans lived across a wide area of Asia, from Siberia to Southeast Asia, and possibly into Oceania. Modern populations in Melanesia and Australia carry significant amounts of Denisovan DNA, up to 5% in some populations, indicating interbreeding occurred when modern humans moved into those regions. Intriguingly, some of the DNA modern humans inherited from Denisovans appears to have been beneficial. A gene variant found in modern Tibetans and inherited from Denisovans helps them thrive at high altitudes by affecting how their bodies respond to low oxygen levels. This is direct evidence that interbreeding with archaic humans provided modern humans with advantageous genetic variants that helped them adapt to new environments as they spread around the world. The relationships among Neanderthals, Denisovans, and modern humans are turning out to be more complex than a simple branching tree. Recent DNA evidence suggests that these species interbred with each other multiple times in multiple regions, creating a complex web of genetic exchange. Some Neanderthals show evidence of Denisovan ancestry. Modern humans show evidence of multiple waves of interbreeding with Neanderthals. There are even hints in the DNA of a ghost population, another archaic human species that contributed genes to Denisovans, and possibly to modern humans in Africa, though we have no fossils that can be definitively assigned to this mysterious population. This picture of repeated interbreeding has profound implications for how we think about human evolution and about what it means to be human. The different human species weren't completely isolated, unable to interbreed. When they met, they sometimes produced viable, fertile offspring whose genes contributed to later populations. The boundaries between species were real, but somewhat porous. We are not purely Homo sapiens, but carry within us genetic echoes of multiple human species. A living reminder that the human story is not one of isolated development, but of a complex web of relationships spanning hundreds of thousands of years and thousands of miles. The arrival of Homo sapiens. After this long journey through the deep past, through the Australopithecines, and early Homo and Homo erectus, and the middle chapter species, we finally arrive at ourselves. Homo sapiens, anatomically modern humans, the species to which every person reading these words belongs. When and where did our species emerge? Until recently, The oldest widely accepted fossils of Homo sapiens came from Ethiopia, from sites called Omo Kibish and Herto, dated to about 195,000 years ago. These fossils show the characteristic features of our species: high, rounded skulls, vertical foreheads without prominent brow ridges, relatively flat faces, and chins on the lower jaw, a feature that's unique to modern humans and absent in all other human species. But in 2017, a remarkable discovery pushed the origin of our species significantly further back. At Jebel Ir-Houd in Morocco, researchers found fossil remains including partial skulls and other bones dated to about 300,000 years ago using multiple independent dating methods. The skulls show a mix of modern and more archaic features. The faces are relatively flat and modern-looking, but the skulls are longer and lower than in later modern humans, and the brow ridges are more prominent. Yet the overall combination of features is distinctly Homo sapiens, suggesting these are among the earliest members of our species. The Jebel Ir-Houd discovery, combined with other fossil evidence from across Africa, has led many paleoanthropologists to revise their thinking about the origin of our species. Rather than emerging from a single population in a single location in Africa, Homo sapiens appears to have evolved from interactions among diverse populations spread across the African continent. Different populations developed different modern features at different times. Periodically, changing climates and shifting landscapes would have brought populations into contact, allowing gene flow and the mixing of traits. Gradually, over tens of thousands of years, the constellation of features we recognize as anatomically modern humans emerged from this Pan-African process. This model, sometimes called the African multi-regional model, or the multiple populations model, emphasizes that human evolution was not a simple progression in a single line, but a complex process involving many populations exchanging genes and traits across a diverse continent. Africa's varied environments, from rainforests to deserts to grasslands, from mountains to coastlines, provided diverse selective pressures that shaped different populations in different ways, while maintained enough contact to remain part of a single evolving species. The stone tools associated with these early Homo sapiens show significant advancement over earlier technologies. The Middle Stone Age toolkit, which appears about 300,000 years ago in Africa, includes refined blades and projectile points that could be hafted onto wooden shafts to create sophisticated hunting weapons. These tools required careful planning and precise technique to manufacture, demonstrating cognitive abilities equal to those of modern humans. But having the anatomy and basic cognitive abilities of modern humans doesn't necessarily mean behaving in ways we would recognize as fully modern. There's an important distinction made by archaeologists between anatomically modern humans and behaviorally modern humans. Anatomically modern humans have the skull shape, brain size, and overall anatomy of people today. Behaviorally modern humans exhibit the full range of cultural and symbolic behaviors that characterize human societies: complex language, abstract art, music, elaborate burials with grave goods, long-distance trade, sophisticated tools made from diverse materials, personal ornamentation, and the transmission of complex cultural knowledge across generations. The archaeological evidence suggests that behavioral modernity emerged gradually in Africa, with different elements appearing at different times and in different places. By 100,000 years ago, there's clear evidence of complex behaviors at Blombos Cave in South Africa, including engraved ochre pieces that appear to be deliberate designs, carefully crafted bone tools, and shells pierced for use as beads, indicating personal ornamentation. Sites at Pinnacle Point, also in South Africa, show use of coastal resources and sophisticated knowledge of fire and heat treatment of stones to improve toolmaking. By 70,000 to 80,000 years ago, the archaeological record in Africa shows a flourishing of symbolic behavior, including elaborate burials, clear artistic expression, and a diversity of tool technologies adapted to different environments. This doesn't mean earlier populations weren't behaviorally complex, only that the evidence becomes clearer at this point. Some archaeologists argue that behavioral modernity emerged much earlier, possibly concurrent with anatomical modernity, but that the evidence is hard to preserve or recognize in the earlier part of the archaeological record. During the period from 300,000 to 100,000 years ago, Homo sapiens remained in Africa, evolving and developing the behaviors that would characterize our species. The populations were not large. Genetic evidence suggests that the effective population size of humans during this period was quite small, perhaps only tens of thousands of breeding individuals. Multiple times during this period, human populations appear to have declined dramatically, possibly in response to climate events like severe droughts. At one point, perhaps 70,000 to 80,000 years ago, the human population may have been reduced to just a few thousand individuals. A genetic bottleneck that's reflected in the relatively low genetic diversity of modern humans compared to many other primate species. Yet despite these challenges, despite their small numbers and their confinement to a single continent, these early Homo sapiens were developing something remarkable, a capacity for symbolic thought and cultural transmission that would eventually allow them to spread across the entire world, adapt to every environment from Arctic tundra to tropical rainforests, and become the most successful large mammal the planet has ever seen. But that story of expansion, that story of how we became a global species, would not begin until relatively recently in the grand time scale of our species' existence. The Great Migration, leaving Africa. For the first 200,000 or more years of our species' existence, Homo sapiens remained in Africa. Then, sometime between 100,000 and 70,000 years ago, something changed. Small groups began to leave the continent, moving into the Middle East and eventually spreading across Asia, Europe, and eventually to Australia and the Americas. This dispersal, often called the out-of-Africa migration, represents one of the most significant events in human history, the beginning of our species' transformation from a regional African population into a global presence. The earliest evidence for modern humans outside Africa is somewhat ambiguous and debated. Fossils from Skul and Kafse caves in Israel, dated to about 120,000 to 90,000 years ago, show anatomically modern humans living in the Middle East. However, this population doesn't appear to have been the source of later non-African humans. They may represent an early, unsuccessful attempt to expand beyond Africa that ended in local extinction, or they may have remained isolated in the Levant without spreading further. The main expansion that led to all modern non-African populations appears to have occurred later, perhaps around 70,000 to 60,000 years ago, based on both genetic and archaeological evidence. Modern human fossils and artifacts begin appearing in Asia and Australia by 70,000 to 65,000 years ago, requiring that the migration out of Africa occurred before then. Genetic evidence, including both nuclear DNA and mitochondrial DNA, points to a dispersal around this time as well, with all non-African populations tracing their ancestry back to a relatively small founding population that left Africa during this period. What prompted this expansion? We can only speculate, but several factors may have contributed. Climate change might have opened corridors through otherwise inhospitable regions, allowing movement into new areas. Population pressure in Africa might have pushed groups to seek new territories. Or perhaps humans simply reached a threshold of technological and cognitive sophistication that made them capable of adapting to new environments effectively. The development of more sophisticated clothing, better understanding of how to find and process diverse foods, improved hunting technologies, better social organization, all these might have contributed to the ability to expand into new territories. The route or routes taken by these migrating populations remain debated. One hypothesis suggests movement through the Nile Valley and across the Sinai Peninsula into the Middle East. Another proposes a southern route across the mouth of the Red Sea during a period of low sea levels, then along the coastlines of Arabia, India, and Southeast Asia. DNA evidence suggests there may have been multiple waves of migration, with different populations following different routes at different times. What's remarkable is the speed, in evolutionary terms, with which humans spread once the expansion began. By 65,000 years ago, humans had reached Australia, requiring sophisticated boats capable of crossing significant stretches of open ocean to reach the island continent. By 45,000 years ago, humans were in Europe. By 15,000 years ago, perhaps earlier, humans had crossed into the Americas, completing the colonization of all continents except Antarctica. This rapid expansion was made possible by a crucial characteristic of our species: behavioral flexibility. Rather than being narrowly adapted to a specific environment, humans could observe new situations, experiment with new strategies, and transmit successful innovations to others through culture. When humans encountered a new environment, they could figure out what plants were edible, what animals could be hunted, what materials could be used for tools and shelter. They could adapt their behavior without waiting for biological evolution to change their bodies. But the expansion out of Africa wasn't simply humans moving into empty landscapes. In many regions, other human species were already living there. In Europe and Western Asia, humans encountered Neanderthals. In Asia, they encountered Denisovans and possibly other archaic human populations. These encounters led to interbreeding, as we've discussed, leaving genetic signatures that persist in modern populations. but they may also have led to competition for resources. And ultimately, the other human species disappeared within tens of thousands of years of modern humans' arrival. The expansion also had dramatic effects on other species. Many large animals, the megafauna, went extinct shortly after humans arrived in various regions. In Australia, giant marsupials, enormous flightless birds, and massive reptiles all disappeared within a few thousand years of human arrival. In the Americas, mammoths, mastodons, giant ground sloths, saber-toothed cats, and many other large species vanished within a similar time frame of human colonization. The extent to which human hunting caused these extinctions versus climate change or other factors remains debated, but there's a clear correlation between human arrival and megafaunal extinction that's hard to ignore. As humans spread into diverse environments, natural selection began operating on the dispersed populations, leading to regional adaptations. Populations in northern latitudes evolved lighter skin, an adaptation that allows more efficient production of vitamin D in environments with low sunlight. Populations at high altitudes evolved genetic adaptations for dealing with low oxygen levels. Different populations developed different patterns of digestion, with some populations evolving the ability to digest lactose in adulthood, allowing them to exploit dairy products from domesticated animals. These regional variations emerged relatively recently, within the last 60,000 years, showing that human evolution didn't stop once we became anatomically modern, but continued in response to new environments and new challenges. Yet despite these regional variations, all modern human populations remain part of a single species, capable of interbreeding and producing healthy, fertile offspring. The genetic differences between populations are relatively small, a reflection both of our recent common origin in Africa and of the continued gene flow between populations that has prevented isolation and speciation. We are, at a genetic level, one of the most uniform species on the planet, a consequence of our rapid expansion from a small founding population and our uniquely mobile and interconnected nature. What made us different? With the story of our origins and expansion now told, we can step back and ask a fundamental question. What made Homo sapiens different? Why did our species survive and spread across the globe while other human species, including the sophisticated Neanderthals and the widespread Homo erectus, ultimately disappeared? What do we have that they lacked? The answer is not simple, and it's certainly not about intelligence in some crude sense. Neanderthals had brains as large as ours. Homo erectus survived for nearly 2 million years, far longer than our species has been around. All of these species were intelligent, adaptable, capable of complex behavior. The differences are more subtle, lying in the details of cognition, social organization, and cultural transmission. One crucial difference appears to lie in the realm of symbolic thinking and language. While Neanderthals showed some capacity for symbolic behavior, the archaeological record left by Homo sapiens is drenched in symbolism from an early date. Our ancestors created elaborate art, from cave paintings to carved figurines to engraved bones. They made jewelry and personal ornaments, objects whose value lies not in practical function but in symbolic meaning. They buried their dead with grave goods, suggesting beliefs about an afterlife. They traded objects over long distances, creating far-flung networks of exchange. This facility with symbols may reflect a difference in how our brains process abstract concepts. Symbols allow us to represent things that aren't physically present, to think about the past and future, to share complex ideas that can't be directly observed. Language, the ultimate symbolic system, allows us to transmit knowledge with incredible precision and efficiency. A skilled individual can explain to others not just what to do but why, can describe processes and relationships and abstract concepts, can build on the knowledge of previous generations in ways that would be impossible without language. Recent research suggests that something fundamental changed in how our species processes and transmits culture. While other animals, including other human species, can learn from each other, Homo sapiens appears uniquely capable of cumulative cultural evolution, the ability to build on innovations across generations, gradually refining and improving technologies and behaviors over time. Each generation doesn't start from scratch, but inherits the accumulated knowledge of all previous generations, allowing a continuous ratcheting up of complexity. This capacity for cumulative culture may be related to differences in social organization. There's evidence that modern humans formed larger, more interconnected social networks than Neanderthals. Analysis of the internal structure of Neanderthal skulls suggests they devoted more brain volume to visual processing and body control, possibly at the expense of areas devoted to social cognition. Modern humans may have been better at maintaining relationships across larger groups, at forming alliances, at coordinating activities among many individuals. Larger social networks would have provided multiple advantages. More individuals means more potential innovators, more chances for someone to stumble upon a useful new technique or strategy. More connections between groups means innovations can spread more quickly, and valuable information about resources, threats, and opportunities can be shared across wide areas. Larger networks also provide more potential mates, reducing problems with inbreeding and increasing genetic diversity within populations. There's also the question of behavioral flexibility and creativity. While it's difficult to assess these traits from fossils and artifacts, there are hints that modern humans were particularly good at adapting to new situations. When we moved into new environments, we relatively quickly figured out how to exploit them. We adapted our tools, our hunting strategies, our dietary habits to whatever the local conditions required. We were generalists in the best sense, capable of thriving in tropical rainforests, temperate grasslands, Arctic tundra, and everything in between. This flexibility may stem from how our species handles innovation and risk-taking. There's evidence from the archaeological record that modern humans experimented more than other human species, trying new materials for tools, new hunting techniques, new ways of organizing living spaces. Not all experiments succeeded, but the willingness to try new approaches, combined with the cultural transmission mechanisms to spread successful innovations, created a species unusually capable of adapting to change. Another factor that's been proposed is the role of long-distance exchange networks. Modern human sites show materials that originated hundreds of miles away, particular types of stone for tool-making, shells from distant coasts, materials that must have been traded through multiple groups to reach their final destination. These exchange networks did more than just move materials. They moved information, ideas, innovations. They created connections between widely separated populations, reducing isolation and increasing the flow of genetic and cultural information. The development of more sophisticated projectile weapons may also have played a role. There's evidence that modern humans developed the bow and arrow earlier than Neanderthals, and also used spear throwers that could launch projectiles with greater force and accuracy than could be achieved by hand. These weapons allowed hunting from a distance, reducing risk and potentially increasing success rates. The mental capabilities required to manufacture and use these weapons, planning, precision, understanding of trajectories and forces, may reflect broader cognitive differences as well. It's important to note that we are not saying Neanderthals or other human species lacked these capabilities entirely. The differences were likely matters of degree rather than absolute presence or absence. Neanderthals had language or something like it. They had symbolic behaviors. They cared for their group members. They had sophisticated technologies. But in each domain, modern humans may have had a slight edge, and those slight edges, accumulated across many domains, may have been sufficient to make the difference between survival and extinction. We must also acknowledge the role of chance. History is full of contingencies, moments where things could have gone differently. Perhaps modern humans survived and spread partly because of luck, the right innovations appearing at the right times, the right climate conditions allowing expansion at crucial moments, the right founder populations carrying beneficial genetic variants. A different roll of the cosmic dice, and perhaps Neanderthals would be writing histories of their evolution, pondering why those modern humans from Africa didn't survive. The last survivors. Why only us? Of the many species of humans that walked the earth over the last 2 million years, we alone remain. Homo erectus, with their nearly 2 million year run of success, are gone. The Neanderthals, so well adapted to Ice Age Europe, vanished. The Denisovans, mysterious inhabitants of Asia, disappeared. The late surviving hobbit humans of Flores Island in Indonesia, Homo floresiensis, went extinct around 50,000 years ago. Even recently discovered species like Homo luzonensis from the Philippines, which may have survived until 50,000 years ago, eventually died out. By 30,000 years ago, and possibly as early as 40,000 years ago, Homo sapiens was the only human species remaining on Earth. This is an unusual situation. For most of the past 2 million years, multiple human species coexisted, living in different regions, adapted to different conditions. The presence of only a single human species is a recent and perhaps temporary condition in the grand sweep of human evolution. Why did all the other human species disappear? This question has spawned extensive research and considerable debate, and the answer is almost certainly different for different species and different regions. There's no single explanation that accounts for all the extinctions. For some species, climate change likely played a major role. The period from about 50,000 to 30,000 years ago saw dramatic climate fluctuations as the as the world moved into the coldest part of the last ice age. Some human populations may simply have been unable to adapt quickly enough to the changing conditions. Their food sources might have disappeared, their habitats might have shrunk, environmental stresses might have reduced population sizes below the threshold needed for viability. For Neanderthals, the arrival of modern humans in Europe correlates closely with their decline, suggesting competition played a role. This doesn't necessarily mean direct violent conflict, though that may have occurred. Instead, the competition might have been indirect, with modern humans more efficiently exploiting resources, gradually outcompeting Neanderthals for territory and food. Given that both species were apex predators hunting similar game and using similar resources, even a slight advantage in hunting efficiency or social organization might have been enough over thousands of years to push Neanderthals toward smaller populations, reduced ranges, and eventual extinction. But the story isn't entirely one of replacement. As we know from genetic evidence, there was also interbreeding. This means the extinction of other human species might be better characterized as absorption rather than pure replacement. Neanderthal genes survive in modern humans. Denisovan genes survive in modern humans. In a sense, these species haven't entirely disappeared but have been incorporated into the genetic makeup of Homo sapiens. The distinct morphological and cultural identity of these species has been lost, but their biological legacy persists. Some researchers have proposed that the extinction of other human species might have been accelerated by diseases carried by modern humans. When isolated populations that have never encountered certain pathogens suddenly come into contact with them, the results can be devastating, as history has shown repeatedly in more recent times. If modern humans carried diseases to which they had some resistance, but to which Neanderthals or Denisovans had never been exposed, it could have contributed to their decline. Reduced population sizes would have made extinction more likely through simple random processes. Small populations are vulnerable to inbreeding, which can increase the frequency of harmful recessive genes and reduce overall fitness. They're vulnerable to random demographic fluctuations, a few bad years, a few unlucky accidents, and a small population can crash. They're vulnerable to loss of genetic diversity, which reduces the raw material for adaptation to changing conditions. And they are vulnerable to stochastic extinction. Pure bad luck can doom a small population even if there's nothing fundamentally wrong with the species. There's a melancholy aspect to being the last surviving human species. We're alone in a way that our ancestors never were. When Homo erectus walked the earth, they shared the world with other human species. When early Homo sapiens evolved in Africa, Neanderthals and Denisovans lived in Eurasia, and possibly other species existed in other regions. But now, there's only us. No other creature with whom we can communicate in language. No other species capable of the kind of symbolic thought and culture that characterize humans. We are the sole representatives of our genus, and all our closest relatives are gone. This loneliness has practical implications as well. Because there's only one human species, we have no living comparison group that could help us understand which aspects of human behavior and cognition are truly universal to the genus Homo and which are specific to our particular species. We can't experimentally test hypotheses about human evolution the way we might with other organisms. Because we can't compare different human species living under different conditions. We're limited to fossils, artifacts, and the somewhat distant comparisons with other primates. Yet this situation also gives us a unique perspective on evolution and diversity. We can look at the fossil record and see that the current state, with only one human species, is atypical. We can understand that our survival is not necessarily a reflection of superiority, but of a complex interaction of adaptations, circumstances, and chance. We can appreciate that the other human species that disappeared were successful in their own right, lasting in some cases for hundreds of thousands or millions of years, and that they contributed to our genetic heritage even as their distinct identities vanished. Conclusion: the ongoing story. As we come to the end of this long journey through time, as we drift back toward the present from our travels among our ancient ancestors, it's worth reflecting on what we've learned and what remains mysterious. We started with a question: who was the first human? And we've discovered that this question doesn't have a simple answer. There was no first human in the sense of a single individual who represents the origin of our lineage. Instead, our story unfolds across millions of years, through countless generations, involving not a single line of descent, but a complex network of related species, all sharing common ancestry, but each taking their own evolutionary path. We've met some of the key characters in this story. Sahelanthropus and Ardipithecus from the deep past, when our lineage was just beginning to diverge from the apes. Lucy and her species Australopithecus afarensis, showing us that upright walking came first before big brains, challenging our assumptions about what made us human. The early members of genus Homo, beginning to use tools more systematically and showing the first expansions in brain size. Homo erectus, the great traveler, who spread across the Old World and surveyed for nearly 2 million years. The Middle Period species like Homo heidelbergensis, leading toward both our own species and our closest cousins. The Neanderthals, sophisticated and successful, whose genes still flow in our veins. The mysterious Denisovans, known more from DNA than from bones, reminding us how much we still have to discover. And, finally, Homo sapiens, emerging in Africa perhaps 300,000 years ago, eventually spreading across the entire world, to become the only surviving human species. The picture that emerges is not one of inevitable progress toward modernity, but of adaptation, experimentation, and diversification. Evolution doesn't have a goal. It doesn't aim toward producing humans or any other particular outcome. It simply responds to immediate pressures, with variations that help survival and reproduction becoming more common, and those that hinder these things becoming less common. The fact that we're here, pondering our origins, is the result of countless contingent factors, small advantages accumulated over time, and no small amount of luck. Recent discoveries continue to reshape our understanding of human origins. New fossils are found regularly, each one potentially revising our understanding of when species appeared, where they lived, how they related to each other. New techniques for extracting and analyzing ancient DNA are revealing relationships and population movements that fossils alone could never show. New dating methods are providing more precise timelines. New analytical techniques are allowing us to extract more information from existing fossils, seeing details of growth, diet, behavior that previous generations of researchers could never access. Some of the most exciting recent discoveries have shown just how diverse the human family was. The discovery of Homo naledi in South Africa, dated to between 335,000 and 236,000 years ago, revealed a species with a strange mix of primitive and modern features, suggesting human evolution was even more complex than we thought. The discovery of Homo luzonensis in the Philippines showed that even island environments in Southeast Asia hosted unique human species. The growing recognition of diversity among early Homo sapiens themselves, with different populations in Africa showing different combinations of modern features, is revising our understanding of how our species emerged. As we learn more, the human family tree looks less like a neat ladder of progress and more like a bushy shrub with many branches, some short, some long, some leading to other branches, many leading nowhere. We happen to be living at a time when only one twig remains, but for most of human evolutionary history, the bush was fuller, with multiple human species coexisting on Earth. This knowledge should inspire humility. We're not the pinnacle of creation, not the inevitable end point of evolution, but rather the current surviving representatives of a diverse group of species that have tried many different ways of being human. Our survival owes as much to circumstance as to any inherent superiority. Our ancestors weren't marching steadily toward us through time, but simply adapting to their immediate environments, responding to pressures they couldn't have understood, making choices whose long-term consequences they couldn't have predicted. Yet this knowledge should also inspire wonder. We're connected through an unbroken chain of descent to the earliest life on our Earth, through our mammal ancestors, our primate ancestors, our hominin ancestors, all the way back to the first self-replicating molecules that sparked the engine of evolution billions of years ago. Every person alive today is the current link in that chain, carrying genes inherited from countless ancestors, some human, some not yet human, stretching back through depths of time that dwarf human history and memory. We're still learning who we are and where we came from. Each new fossil, each new analysis, each new technique adds to our understanding. There are major questions that remain unanswered. We still don't know with certainty which species was our direct ancestor. Was it Homo heidelbergensis, as many think? Or was it some other species or population whose fossils we haven't yet found or properly identified? We don't fully understand what triggered the expansion of modern humans out of Africa, or why we were more successful than other human species. We don't know how much of our behavior and cognition is shared with other human species and how much is uniquely Homo sapiens. We don't know if there are other human species whose fossils remain undiscovered, waiting in some cave or riverbank to surprise future paleontologists. The story of human evolution is ongoing in another sense, too. We're still evolving. Natural selection hasn't stopped acting on human populations. We continue to adapt to our environments, though often now in ways shaped by culture and technology rather than by purely natural forces. Our understanding of our evolution shapes how we think about ourselves, our relationships with each other, and our place in the natural world. It reminds us that we're a part of the living fabric of Earth, connected to all other life through common ancestry and shared biological heritage. As you let these thoughts drift through your mind, as you settle deeper into relaxation, imagine that long chain of ancestors stretching back through time. Each one was a living being like you, with their own experiences, their own challenges, their own moments of fear and joy and wonder. Each one survived long enough to reproduce, passing their genes forward through time until eventually they reached you. You carry their legacy in your bones, in your DNA, in the very structure of your brain. And that chain continues through you. You're not an ending, but a link, connecting the deep past with an unknowable future, carrying forward the story of our species into whatever comes next. It's a profound responsibility and a profound gift. This connection through time, this participation in the grand narrative of human evolution. If you've enjoyed this gentle exploration through the story of human origins, I hope you'll take a moment to like this video and subscribe to Sleepy Answers. Your support helps these peaceful journeys through science reach more curious minds, one sleepy soul at a time, sharing wonder and knowledge in the quiet spaces between waking and sleep. For now, let yourself rest. Let the millions of years we've traveled through settle into gentle images at the edges of your awareness. Let the faces of our ancestors fade into the soft darkness. You've walked through deep time tonight, and now it's time to simply be here in the present moment, connected to all that came before, breathing quietly in the night. Good night.